So we got some questions on word embeddings. So we will be making a small series of videos on that. You might have heard about these word embeddings before though. Typically you hear that there's a story where there's a king and there's a queen and that there's also this man and this woman. And the idea behind word embeddings is that they live, in this case I'm drawing it in a two-dimensional plane, but there are these tokens and they have some numeric vector attached to them. Or you can just say, well, there are these coordinates that are attached, and this is also a numeric description. But what might be slightly amazing is that there appear to be relationships between these word embeddings. So for some reason, we've got king and queen here close together, and we've also got man and woman here close together, and you might wonder, geez, why is that intuitive? So for this video, I thought it might be fun to investigate that. But the way that I'm going to do it is I'm not going to make word embeddings. Instead, what I'm going to do is I'm going to make letter embeddings. And there's a few reasons why I think letter embeddings are more useful now. For starters, they are lightweight, so we can make an exercise that we can actually run within 10 minutes. 2, we have a smaller problem, so there's less complexities to worry about. And we understand letters quite well. There's only a few letters out there, instead of all the possible words that exist. So the goal of this video is to just come up with a way to get a plot that kind of resembles this, but not for tokens, but for letters. There's a couple of ways of achieving this, but we'll first need a dataset. So I found an interesting dataset on Kaggle. It is the A Million News Headlines dataset. It has news headlines that were published over a period of 17 years, and these news headlines, they come from Australia. I'll probably not use all of them, but this is a nice dataset of actual text that appeared somewhere, and that should be somewhat general because it came from a news outlet. But given such a dataset, what are we going to do with it? So I'll just take the first sentence I saw in that dataset. ABBA decides, and the sentence was against community broadcasting license. But let's say that this is the sentence that we have first. Now, what I'm interested in is I'd be interested in saying, take all of these letters and plot them in some two-dimensional space. So again, that's what we see here. I would like to find a nice mapping from something that's a token to something that is numeric. And I would like to have an algorithm do this in a somewhat principled way, such that clusters of letters might appear in places. So here's a approach of thinking about that. What I can do is I can say, you know what? Let's have a sequence of all these letters. So we start with the letter A and then follows the letter B. Then we have the letter B, then we have the letter A. Then we've got A, and then we've got a space, and then we've got a space, and then we get the letter D, and then we get the letter D, and then we get the letter E, and etc., etc., etc. The idea here is, maybe this letter can predict that letter. We could maybe train a neural network to do this for us. So how about we take our letter, and then we pass that through an embedding layer. Now this embedding layer, it will output a vector. Namely, the vector that belongs to that letter. So suppose this was the letter A, then out here comes the vector for that letter A. And this vector is something that it will have to learn. In that sense, this embedding is essentially nothing more than a Python dictionary where this is the key and there's some sort of a value that has to come out. Next, what I could have is I can then say, let's pass that to a dense layer. And this will be a dense layer with a softmax such that it will try to predict which of the letters follow next. And when I say letters, I do mean these tokens. I think there's also going to be some numbers in here, probably. But I'm going to remove everything that's non-alphanumeric. So one might surmise that we have 10 numbers, plus 26 letters, plus the whitespace token. So in total, the algorithm has 37 options to choose from here. Now, the idea behind the approach is as follows. We can split this algorithm up in two pieces. And we can say, well, we've got this embedding part of the algorithm and this prediction part. And since we only have one simple dense layer here, the hope is that eventually, there's going to be gradients and stuff, and we're going to have a system here that learns. But eventually what has to happen is that the mapping from this letter to that embedding, that also has to update. There's not a whole lot that it can correct for here because it's just a simple dense layer. So these embeddings will need to learn something of a meaning. And that meaning is defined by the order in which these letters occur. So I'll program this out right now and highlight some of the algorithmic code. I've made a colab notebook, which I will share in the footnotes, but I figured zooming in on the Keras parts and the machine learning parts would be relevant. So when you look at this code, you will notice that above here I am doing embedding stuff, and down below here I am doing prediction stuff. I've split up my model into two different segments. When I get my token, first what's going to happen is it will get passed to the embedding layer. And then a vector will come out. A vector of size 2. This part is defined in the model embed object. And you'll notice that the embedding layer that's in here, that is also being used in the model there. The difference is that we also put a nice dense layer after it. And what comes out of here is the prediction for the next token. And this entire model, that is called the prediction model. And the main reason for doing that is I can then tell Keras, hey, train this one over here, and then automatically this one will also be trained. Once everything is trained though, what I can still then do is grab this model and call predict on it. And that way I will be able to visualize the embeddings. Again, you'll have access to the notebooks so you can run this yourself, but what I've done is I've actually trained this. And it turns out that if you start this without doing any form of training, this is what the embeddings look like. And then after you do the training, the embeddings look a bit different. After the training, this is what they look like. So let's go back to the whiteboard and think about what this means. So I've drawn the model again here. The model can still be split up into two parts. So we've got this embedding part and this prediction part. And when we started, these were the embeddings that came out of this embedding layer. And after we trained, these are the embeddings that came out of the embedding layer. Now, the way that worked was we have our predictions, and these are being compared to the ground truth. This gives us a gradient, and that will update this dense layer. But after the dense layer, updates should also trickle down to this embedding layer. And it turns out that if you want to predict the next letter, you can't just update this dense layer, you also have to make a representation for every token appear here. And the algorithm figured out if you want to make predictions that then maybe the numbers should be clustered together, and that maybe there are two separate types of letters. And I hope you can imagine that what we've just done for letters, that is something you can also do for words. Doing this for letters is much easier though, because there's just a few of them. If you have this with words, you're going to need a whole lot more. But another thing that I hope you can imagine is, because letters are simple, we only need a simple embedding layer and a simple dense layer over here to train this. We could wonder though, can we maybe improve this? So one thing that I've also done is I've said, you know what? How about we take two characters that follow each other as input, and these two both go into the same embedding layer. So these two are the same. And what if, before sending that to the dense layer, we concatenate those? The idea now is that we have two characters going in, so now we're not predicting the second character, now we are predicting the third one over here. But potentially you could argue that there is just that little bit extra information here. The original model only got about 20% accuracy. And you can imagine that if we have not one, but two vectors going out here, that then we should be able to learn a slightly different representation. Note that these two embeddings, they are the same. So when there's a gradient update, the same mapping will get an update, but they will now get two updates, so to say. So with a new model, I would also expect that the embeddings change. These should be different now. So I was curious about this, which is why I was training a new neural network. One that does exactly this. And here's the results. Now we see similar things. So we see that all the numbers are clustered together. The vowels and consonants also demonstrate very similar behavior. So you might wonder, well, what's up with all this white space over here? Because we didn't see that there. What's happening here is we still had one extra character, which was the spacebar. And odds are that the spacebar is somewhere along over here. And that definitely also makes sense. It's supposed to be something that's rather different from all the other clusters. I've also checked the statistics, and it turns out that a model that has 2 tokens going in has about a 22% accuracy, which is definitely higher than what we saw before. The question is, though, what's the result here? Do we care the most about having a good metric at the end? Or do we perhaps care just a bit more about these embeddings, that these are useful in general? This is something that is at the crux of word embeddings in general. And the example here, I've got simple letter embeddings, but the goal of this entire game is that we try to find embeddings that generalize very, very well. We have clusters forming with letters, and these clusters have meaning. The hope is that when you apply a similar approach to words as opposed to letters, that you'll also get meaningful vector representations. Figuring out which word embeddings are very useful is tricky business though. Very often word embeddings are trained on a very large corpus. So you could say, hey, download Wikipedia and get us some word embeddings from that. But then we also have the algorithm that we use. We might be able to say, hey, there's more than just one language task here. Maybe we don't want to predict the next token, but maybe we'd like to say, hey, there's 2 tokens from the future and 2 tokens from the past, and I want you to predict the center one. So you can imagine that there are many variants, not just because the algorithm is different, but also that the dataset that it's trained on is different. The hope is that you can train on something that represents the English language, and then come up with word embeddings that can be applied in many different use cases. The best numeric representation for a language is still an unsolved problem, and the field is quite active. People are figuring out new embeddings all the time. But let's wrap up for now. I hope you enjoyed this introduction to word embeddings. The goal was to show a small experiment that you can run yourself to hopefully get some intuition going. In real life, we are not going to train for letter embeddings, but what we will do is something very similar. The relationship from a letter to a word is similar to how a word relates to a sentence or a document. In the next video, I will attempt to train a proper word embedding using the same dataset by training a variant of the glove algorithm. I hope you'll stay tuned for that.